All right, welcome ladies and gentlemen. This is our first video in our moles, reactions, and Stoich unit. In this video, I'm going to be talking about two additional mole conversions we can do, grams to moles and vice versa, and volume of a gas, basically liters to moles and vice versa, because we already talked about particles to moles in class. So we're going to have a total of 3 conversions to do with the mole. You will need your reference table and you will need a calculator to follow along with this particular video. So mole mass conversions, this is based on the atomic masses that are in the periodic table, because you look up carbon, one atom of carbon has a mass of 12.0 AMU. Remember atomic mass units, but remember from the Pogel, that also means that 1 mole of carbon, again when we switch from atoms to moles, it has a mass of 12.0 grams. It's the same number, we've simply changed the unit. We've scaled everything up by making it a mole instead of a single atom. 1 molecule of HCl will have a mass of, well, how do we figure that out? Then we need to break it down into the H and the Cl and add them together, and hydrogen is 1.0 and chlorine is 35.5. So adding them together, 1 molecule of HCl has a mass of 36.5 atomic mass units, AMU, but a mole of hydrochloric acid has a mass of 36.5 grams. So the big point here is that the mass of a mole is a number that we get from the periodic table. It's the same number as atomic mass. We've simply scaled everything up, so we've changed the unit from AMU to grams when we talk about 1 single thing versus an entire mole of that thing. Well, this is important because this is exactly how we do mole to mass conversions. Molar mass, or gram formula mass, the thing that we talked about where you sum all the masses together like we were just doing, has a unit of grams per mole. What does that mean? That means that that number is the number of grams in 1 mole of a given substance. And we can use that as a conversion factor to convert between grams and moles. So if you have a question that's asking for grams and it gives you moles, we are going to use the gram formula mass of that compound, because the gram formula mass of that compound tells you the number of grams that are in 1 mole of that particular substance. So it's a conversion factor. Water, as an example, has a gram formula mass of 18 grams per mole because it's water. So it's H plus O, so that's 1.0 plus 1.0 plus 16.0. Well, you get that number and it's 18. So what does that 18 mean? It means 18 grams per mole, which means that in 1 mole of water, we have a mass of 18 grams. 18 grams means 1 mole. 1 mole is equal to 18 grams. It's a conversion factor, right? It's saying how many what and what. For water, it's saying how many grams in a mole. For water, it says 18 grams in 1 mole. So we can use T-charts to figure this out. So as an example, how many grams are in 3.0 moles of CH4? So what is the mass of 3.0 moles of CH4? Well, for that, we're going to need the gram formula mass, right, of this thing, because we need to know what's the mass of just 1 mole if we want to know the mass of 3 moles. The gram formula mass tells us the mass of 1 mole. So we figure out the gram formula mass. So for CH4, that's carbon plus hydrogen plus hydrogen plus hydrogen plus hydrogen, or 16. 16 grams per mole. What does that mean? That means that 16 grams is equal to 1 mole for this particular compound. Different compounds that have different masses, so it's not going to be the same conversion factor every time. With that in mind, we can now set up our T-chart. So remember, we want to start by drawing the T, and then we want to take the number the problem gives us. Well, the problem is right here, right? This is the question. How many grams are in 3.0 moles of CH4? So this, the 3.0 moles, that's the number the problem gives us. So that's the number that's going to go in the top left-hand corner, 3.0 moles of CH4. And then we want to use the gram formula mass right here, because the gram formula mass tells us that 16 grams is equal to 1 mole. Well, I put moles in the top left-hand corner, so I'm going to put moles bottom right so that it cancels out. And I know from this, how many moles? 1 mole. So that way, right, moles have gone away. And then what goes on the top? The other part of the conversion factor, so the 16 grams. 1 mole of CH4 is equal to 16 grams. So what's the math that we're doing? Well, we're going to multiply 3 times 16, because remember we multiply our top numbers together, then we divide by the bottom, and then we're dividing by 1. So 3 times 16, that's 48. Divided by 1 is just 48. And what unit? Grams. We're left with grams because we didn't cancel that. So that's our answer, 48 grams, which should make sense. If 1 mole weighs 16 grams and we have 3 moles, it should make sense that we want to triple that to get the mass of 3 moles. So another example, how many moles are in 176 grams of sodium chloride? Well, same thing, same idea here. We have, that's asking for moles, it gives us mass. So that means that we need GFM, because gram formula mass is how we do this mole to mass or mass to mole conversion. So what do we need the gram formula mass of? We need the gram formula mass of sodium chloride, because that will tell us how many grams are in 1 mole. It tells us the number of grams in 1 mole. So with that gram formula mass, let's see, we've got Na and Cl, so we've got to simply add together the Na, which is 23.0, and the Cl, which is 35.5. Remember, take your gram formula masses to the 10th, please. You don't want to round chlorine to either 35 or 36. Nope, it's 35.5. So summing those together, we get 58.5 grams per mole. What does that mean? That means that for NaCl, and remember, gram formula mass is different for every compound. For NaCl, 58.5 grams is equal to 1 mole of sodium chloride. This is our conversion factor, right? Gram formula mass. This is our conversion factor right here. So now we can set up our T-chart and start doing the math. Well, take the number the problem gives you. What is that number? 176, because the question's right there. So that's the number that's going to go top left, 176 grams of NaCl. And then right here is where we're going to use our gram formula mass. And our gram formula mass right here, 58.5 grams is equal to 1 mole of NaCl. Well, what unit is going to go bottom right? Same unit that went top left. It's always the exact same unit. So grams NaCl, I'm going to do grams NaCl. That way the grams of NaCl will cancel. Well, how many grams of NaCl? Well, that's what the gram formula mass tells you, 58.5 grams of NaCl. 58.5 grams of NaCl is equal to what? It's equal to 1 mole of sodium chloride. So that's what's going to go on the top. So grams of NaCl is going to cancel out. And then I'm simply going to do my math. Now, this is why T-charts are awesome, because you don't have to worry, well, am I multiplying or am I dividing? The T-chart will tell you what to do. So I'm going to do 176 times 1, which is 176, then divide it by the 58.5. When we do that, I get 3.01 moles of sodium chloride, which also should make sense, because the gram formula mass tells us that 1 mole is 58.5 grams. So if I have 176 moles, 176 grams, I expect that to be more than 1 mole, right? Because 1 mole is only 58.5 grams, and if I got 176, well, that's obviously more than 1 mole. So the answer makes sense. And then our next conversion, STP. STP, remember, stands for standard temperature and pressure, and we use this to talk about gases, and it's the idea that we have agreed upon conditions, scientists have agreed upon conditions, so that we can standardize our discussion of gases. And table A is where we have the conditions for STP. They are 0 degrees Celsius and 1 atmosphere of pressure, or 101.3 kPa, or 273 Kelvin. Right, but they're just agreed upon conditions. And when gases are under agreed upon conditions, then Avogadro's hypothesis holds true, which says that equal volumes of gases at the same temperature have equal numbers of particles. Well, numbers of particles, that's the mole, because a mole is about how many particles you have. The definition of a mole is 6.022 times 10 to the 23rd particles in 1 mole. That's a mole. So putting it another way, Avogadro's number for gases, so this is only true for gases, it's not true for liquids, but if a gas is at STP, so under these agreed upon conditions, then 1 mole of a gas will always occupy the exact same volume, 22.4 liters. Putting it another way, this is our third conversion factor. 1 mole of gas that is at STP will be equal to 22.4 liters of that gas. It does not matter the identity of the gas. The identity of the gas is irrelevant. This is true of all gases that are at standard temperature and pressure. So any gas at STP will occupy, if it's 1 mole of a gas, it will occupy the exact same volume, 22.4 liters. This is kind of the idea that if you have 4 tires in your car and the tires are all the same volume, then you kind of naturally expect them to all have the same amount of air in the tire. This is sort of the same idea, that if you have 1 mole of a gas, it doesn't matter what the gas is, it's always going to occupy the same space, the 22.4 liters. And we just worked out that it's 22.4 liters. So just a sample problem of this with this to close. You have 0.375 moles of oxygen gas at STP. Oh, that's a nice thing right there, letting us know that we're going to use our new conversion factor. What volume will this gas occupy? What volume? So that tells us that we need liters. The question is asking for liters. It gave us moles. It also told us that it's oxygen gas. However, that is completely irrelevant. It doesn't have to be oxygen. It could be carbon dioxide, it could be nitrogen, could be anything. So it gave us liters, it gave us moles, we're looking for liters. So we can use, the 1 mole is equal to 22.4 liters of a gas at STP. This is our conversion factor. Again, doesn't matter the gas. So we can set up our T-chart. Take the number the problem gives us. What's the number the problem gives us? 0.375 moles. So that's going to go top left. Then we're going to use our conversion factor here, which in this case is going from moles to liters. So what unit did I put top left? I put moles top left, so I can put moles of a gas bottom right. And how many moles of gas? Well, 1 mole, right? That's that portion of the conversion factor. So what's going on the top if I'm looking for liters? 22.4 liters is going on the top, the second half of the conversion factor. So moles top left, bottom right, it cancels out. Then we're multiplying together 0.375 times 22.4. When you do this, you should get, I think, 8.4. But this value here has 3 significant figures. This value here, right, the conversion factor, which by the way never counts towards sig figs, but that also has 3 significant figures. So we base this off the number in the problem, right? It's got 3 sig figs in the problem. So if I want to make my 8.4 have 3 significant figures, I'm going to add a 0 at the end to give it that additional sig fig. Because remember, we always want our answer to have the same number of significant figures as the value in the problem that has the least number of sig figs, but there's only 1 number in this problem, so it has to match. Now, 8.40, what unit is this going to be? It's going to be liters, right? Because that's the unit that I didn't cancel. So there we go. There's that value. And again, so now we've seen a total of 3 conversion factors that we can do with the mole, and we're going to be practicing with this in class.